At the end of this video, you should be able to summarize Kepler's 3 laws of planetary motion and describe how Newton explained Kepler's laws of motion. Chapter 27, Section 2, Kepler's Laws. 20 years before Galileo used a telescope, a Danish astronomer named Tycho Brahe made detailed observations of the solar system. After Tycho's death, one of his assistants, Johannes Kepler, discovered patterns in Tycho's observations. These patterns led Kepler to develop 3 laws that explained planetary motion. Law of ellipses. Kepler's first law, the law of ellipses, states that each planet orbits the sun in a path called an ellipse, not in a circle. An ellipse is a closed curve whose shape is determined by 2 points, or foci, within the ellipse. In planetary orbits, one focus is located within the sun. No object is located at the other focus. The combined length of the 2 lines, one from each focus to any one point on the ellipse, would always be the same as the length of the 2 lines from each focus to any other one point on the same ellipse. Elliptical orbits can vary in shape. Some orbits are elongated ellipses. Other orbit shapes are almost perfect circles. The shape of an orbit can be described in a numerical form called eccentricity. Eccentricity is the degree of elongation of an elliptical orbit, symbolized by lowercase e. Eccentricity is determined by dividing the distance between the foci of the ellipse by the length of the major axis. Therefore, the eccentricity of a circular orbit is E is equal to 0. The eccentricity of an extreme elongated orbit, or parabolic orbit, is E is equal to 1. Law of equal areas. Kepler's second law, the law of equal areas, describes the speed at which objects travel at different points in their orbits. Kepler discovered Mars moves faster in its elliptical orbit when it is closest to the Sun. He calculated that a line from the center of the Sun to the center of an object sweeps through equal areas in equal periods of time. This principle is illustrated on the screen now. Imagine a line that connects the center of the Sun to the center of an object in orbit around the Sun. When the object is near the Sun, the imaginary line is shorter. The object moves relatively rapidly, and the line sweeps through a short, wide, pie-shaped sector. When the object is far from the Sun, the line is long. However, the object moves relatively slowly when it is far from the Sun, and the imaginary line sweeps through a long, thin, pie-shaped sector in the same period. Kepler's second law states that equal areas are covered in equal amounts of time as an object orbits the Sun. Law of periods. Kepler's third law, the law of periods, describes the relationship between the average distance of a planet from the Sun and the orbital period of the planet. The orbital period is the time required for a body to complete a single orbit. According to Kepler's third law, the cube of the average distance, represented by A, of a planet from the Sun is always proportional to the square of the period, represented by lowercase p. The mathematical formula that describes this relationship is k times a cubed is equal to p squared, where k is a constant. When distance is measured in astronomical units, AUs, and the period is measured in Earth years, k is equal to 1, and therefore a cubed is equal to p squared. Scientists can figure out how far away the planets are from the Sun by using this law, because they can measure the orbital periods by observing the planets. Jupiter's orbital period is 11.9 Earth years. The square of 11.9 is 142. The cubed number that is equal to 142 is 5.2. So, Jupiter is 5.2 AUs from the Sun. Newton's explanation of Kepler's laws. Isaac Newton asked why the planets move in the ways that Kepler observed. The explanation that Newton gave described the motion of objects on Earth and the motion of the planets in space. He hypothesized that a moving body will remain in motion and resist a change in speed or direction until an outside force acts on it. This concept is called inertia. For example, a ball rolling on a smooth surface will continue to move unless a force causes it to stop or change direction. Newton's model of orbits. Because a planet does not follow a straight path, an outside force must cause the orbit to curve. Newton gave this force the name gravity, and he realized that this attractive force exists between any two objects in the universe. The gravitational pull of the Sun keeps objects, such as the comet shown here, in orbit around the Sun. While gravity pulls an object toward the Sun, inertia keeps the object moving forward in a straight line. The sum of these two motions forms the ellipse of a stable orbit. The farther from the Sun a planet is, the weaker the Sun's gravitational pull on the planet is. So, the outer planets are not pulled toward the Sun as strongly as the inner ones are. As a result, the orbits of the outer planets are larger and are curved more gently, and the outer planets have longer periods of revolution than the inner planets do. At this point, you should be able to summarize Kepler's 3 laws of planetary motion and describe how Newton explained Kepler's laws of motion.